Good day, everyone. So for today, I will discuss two lessons, which is allylic bromination and the atmospheric chemistry and the ozone layer. Now let's talk about allylic bromination. So what is allylic bromination? Allylic bromination is a chemical reaction where a hydrogen atom on the allylic position of an alkene is replaced with a bromine atom. The allylic position is the carbon atom adjacent to a double bond. This reaction is commonly carried out using bromine Br2 in the presence of a radical initiator like heat or light, or using N-bromosuccinimide NBS as a bromine source. So let's talk about the mechanism of the allylic bromination. The reaction proceeds via a freed radical mechanism. Number 1 is the initiation. Formation of bromine radicals Br under heat or UV light. A bromine radical obstructs an allylic hydrogen, generating an allylic radical, which is stabilized by resonance. The allylic radical then reacts with another bromine molecule to form the brominated product and regenerate the bromine radical. Next is termination. Radical recombination steps that end the chain reaction. So what are the reagents and conditions of the allylic bromination? Br2 plus heat over light or light is equal to direct bromination. NBS in CCl4 or carbon tetrachloride under UV or light, a safer, more selective option for allylic bromination. NBS provides a controlled slow release of Br2 in solution. So where do we apply allylic bromination? Allylic bromination is used in organic synthesis to prepare brominated intermediates, which can undergo further reactions like substitutions or eliminations. It is particularly useful because the allylic position is more reactive due to resonance stabilization of intermediates. So now let's move on to the next lesson, which is the atmospheric chemistry and the ozone layer. Ozone, or also known as O3, is constantly produced and destroyed in the stratosphere, and its presence plays a vital role in shielding us from harmful UV radiation emitted by the sun. It is believed that life could not have flourished on land without this protective ozone layer, and instead, life would have been restricted to the depths of the ocean. The ability of ozone to protect us from harmful radiation is believed to result from the following mechanism. In the first step above, ozone absorbs UV light and splits into two pieces. In the second step, these two pieces were combined to release energy. There is no net chemical change, but there is one important consequence of this process. Harmful UV light is converted into another form of energy. This process exemplifies the role of entropy in nature. Light and heat are both forms of energy, but heat is more disordered form of energy. The driving force for the conversion of light into heat is an increase in entropy. Ozone is simply the vehicle by which ordered energy, or light, is converted into disordered energy, or heat. Measurements over the last several decades have indicated a rapid decrease of stratospheric ozone. This decrease has been most drastic over Antarctica, where the ozone layer is now almost completely absent. Stratospheric ozone over the rest of the planet has decreased at a rate of about 6% each year. Each year, we are exposed to increasing levels of harmful UV radiation that are linked with skin cancer and other health issues. While many factors contribute to ozone depletion, it is believed that the main culprits are compounds called chlorofluorocarbons or CFCs. CFCs are compounds containing only carbon, chlorine, and fluorine. In the past, they were heavily used for a wide variety of commercial applications, including as refrigerants, propellants, and the production of foam insulation, as firefighting materials, and many other useful applications. They were sold under the trade name Freons. The harmful effects of CFCs on the ozone layer were elucidated in the late 1960s and early 1970s by Mario Molina, Frank Rowland, and Paul Crutzen, who shared the 1995 Nobel Prize. In chemistry, for their work, CFCs are stable compounds that do not undergo chemical change until they reach the stratosphere. In the stratosphere, they interact with high-energy UV light and undergo homolytic cleavage, forming chlorine radicals. These radicals are then believed to destroy ozone by the following mechanism. The second propagation step regenerates a chlorine radical, which continues the chain reaction. In this way, each CFC molecule can destroy thousands of ozone molecules. Awareness of the effect of CFCs led to a ban on their production in most countries as of January 1, 1996, as part of a global treaty called the Montreal Protocol on substances that deplete the ozone layer. As a result, much research has been directed toward finding suitable substitutes, such as the following. Two categories of compounds. Hydrochlorofluorocarbons, HCFCs, are compounds that possess at least one CH bond. Below are a few examples. These compounds are believed to be less destructive to the ozone layer because the CH bond allows them to decompose before they reach the stratosphere.